Hello everyone. So this is our third presentation on chemistry, and this one we're specifically going to talk about water and the special properties of water that enable it to be the basis of life on Earth. In the last presentation we talked about the types of bonds that form molecules, and water is a polar covalent bond. And being a polar covalent bond, it gives us a number of particular properties that enable it to have some special chemical attributes that makes it a good solvent and supports life. So that's what we're going to talk about in this presentation. So water is H2O. So it's one oxygen atom bound to two hydrogen atoms. And the oxygen has 8 electrons, so 2 in the first orbital, 6 in the second. Hydrogen only has 1 electron. So each of the hydrogens shares its 1 electron with the oxygen. So that gives oxygen a stable 8 filled up shell, and hydrogen is stable 2 electrons in its first shell. So, but since the oxygen has so many more protons, it attracts the electrons closer to the oxygen atom than to the hydrogen atom. So again, it's kind of like a tug of war. So these electrons are being shared, but they're not being shared equally, so that they're actually closer to the oxygen than they are to the hydrogen. And what that means is that for a water molecule, the oxygen side of the molecule is actually slightly negative. It's not as negative as an ion, but it has a negative charge. And the hydrogen side of a water molecule is slightly positive. This little symbol here is the Greek letter delta, and it means partial charge, and that's when you'll see that sometimes to indicate the charge. So every molecule of water has these slight charges. The oxygen side is negative, the hydrogen side is positive. And why that is particularly important with water is that that means one water molecule is attracted to another water molecule. So you have this plus charge on this water molecule, which is going to be attracted to the oxygen of another water molecule. And that's what's shown here. The red represents oxygen, the white is hydrogen. So this hydrogen is attracted to that oxygen and this one to it. And so what happens is that water kind of is attracted to other water molecules. Those connections between the hydrogens and the oxygens of one molecule and another are called hydrogen bonds. So they're a weaker bond than a covalent or ionic, and it's not holding one molecule together, but it's between molecules, so between one water and another water. But because of those hydrogen bonds, water molecules kind of are attracted to each other and they stick together, and that gives them some special properties that we're going to be talking about. So the hydrogen bonds form when the slightly positive hydrogen is attracted to the slightly negative oxygen. And again, they're weaker bonds than either covalent. So it's between the oxygen of one water and the hydrogen of another water molecule. We're going to talk about some of the properties of water, and almost all of these properties are related to the fact that water is this polar covalent molecule and it attracts to one another. One is that water is a good solvent. And remember, a solvent is things you can dissolve things in. So if we had a beaker of water and we put some sodium chloride in it, which is salt, that sodium chloride is going to come apart and form sodium ions and chloride ions. And the sodium ions are going to be attracted to the oxygen side of the water. And the chloride ions are going to be attracted to the hydrogen side of the water. And so that's how things dissolve. They kind of break up the attraction between the ions. Water is the only solvent in living things on Earth. And so all of inside and outside of our cells, the solvent is water. And so everything that we have to get transported around in our body is transported in water. Another property of water is that water remains liquid at a broad range of temperatures. And in order to boil water, so you have all these water molecules attracted to one another, in order to turn it into steam or water vapor, you have to break all those hydrogen bonds. So it requires a lot more energy to do that, so that it takes more energy to change from liquid water to water vapor. And that's because of the hydrogen bonds. Likewise, when you heat up water, it takes it much longer to cool down. This is important in terms of the Earth, of heating large bodies of water like our Pacific and Atlantic Oceans. They get heated up. It takes them a long time to cool down, and that's important in keeping the climate of our planet livable. Also, water is a component in many reactions inside of our body, and we'll talk more about those later. So again, these hydrogen bonds is the fact that the oxygen of one water molecule is attracted to the hydrogen of another water molecule. And the hydrogen bonds is that right here, the attraction between two. That makes water almost kind of sticky. The fact that water molecules stick together is called cohesion. And it is important in plants' ability to transport water. We don't really talk much about plants from the roots to their leaves. It's the reason that there's like a surface on water, because the water is all sticking to each other. Water molecules will also kind of stick to other things. That's called adhesion. So cohesion is water to water sticking. Adhesion is water sticking to other things like the side of a test tube. And so the cohesion causes surface tension, and that's the kind of film that's on the top of water. You're going to be doing some things in one of your labs to look at some of these. So that's why these little insects can walk across the surface of water, is because there's almost like a film where the water molecules are sticking together. And this water strider bug does not break those bonds. The mass is not enough. We would, if we tried walking on it, our force would be more than the hydrogen bonds could take. So that would lead to the water surface tension being disruptive. And it's the same reason that water kind of forms beads. If you ever noticed when water drops, like on the surface of a car, it forms like drops rather than spreading. And that's because the water is sticking to itself. So it's kind of forming a bead rather than spreading on a flat surface. As we mentioned before, water is the solvent of life. And so a solution we talked about before is a liquid containing made up of a solvent and a solute. And so the solvent is the dissolving agent. The solute is what you put in it. And for living things on Earth, water is the only solvent in living things. And that's why when they always talk about looking for life on other planets or on Mars, etc., One of the things they always look for to see if there's water there or if there had been water there, because the way our cells work, you would need to have water for life to be supported. And again, here's the sodium dissolving in the water. So you have the sodium ion being surrounded by the oxygen part of water molecules, the chloride, which is negative, being attracted to the hydrogen parts of water molecules. So things that don't have a charge don't dissolve in water. So things like oil, which we'll talk about later, some of its properties, but oil, for example, like vegetable oil, corn oil, are non-polar. So they don't have any charge, and so they're not attracted to the water molecules, and they would not dissolve in water. So generally, polar things that are charged will dissolve in water. Things that are not polar will not dissolve in water. One of the really unique things about water, and it's again due to the hydrogen bonds, with water being a polar molecule, is that water is less dense as a solid. So ice is less dense than liquid water. And that's not true for any other substance. Usually the solid form of a substance is more dense than the liquid form. And what that means is, like, if you have a glass of water and you put ice in it, ice is frozen water, it doesn't sink to the bottom, it floats on the top. And that enables oceans and lakes to not freeze all the way down, because they kind of have a layer of ice on the top which insulates it, and that enables living things underneath to still survive in the water. And it also helps control our climate. So again, this is just a picture. So in ice, the atoms of, or molecules of water, are actually farther apart than they are in liquid water. And so, as this polar bear is demonstrating, that's why the ice is floating on top of the water rather than sinking down to the bottom. A final property of water that we're going to talk about is pH. Technically, pH should be a lowercase p and a capital H. I think the spell check thing kept changing that P to an uppercase P. But technically, the correct way to write pH is a lowercase p, a capital H. And pH is a measure of acidity. It actually stands for the power of hydrogen. That's why the H is capital, because it's H for hydrogen, the atom. And what pH is a measure of is the number or the amount of hydrogen ions in a solution. And again, since all solutions in living things are water-based, so it's the number of hydrogen ions in water. So a hydrogen ion is a hydrogen atom that has had the electron removed, so it has a positive charge. And the more hydrogen ions that are present in a solution, the more acidic it is. And because hydrogen ions are acids, so anything that would increase the hydrogen ion concentration in water would be considered an acid. So for example, HCl is hydrochloric acid. That's the acid our stomach produces. And when it's put into water, it forms H plus and Cl minus. And so since it releases this H plus, it's considered an acid. The pH scale is related to the ionization of water. So we've talked about water, H2O, forming a polar covalent molecule, not an ionic molecule. But in every bottle or liter of water, a very small number of the water molecules actually break down into hydrogen ions. And so if you remove a hydrogen, what you're left with is an O and an H, and that has a negative charge. That's also called a hydroxide ion. So when water ionizes, it forms one hydrogen ion and one hydroxide ion in equal concentrations. So water is considered to be neutral because it has equal numbers. If you were to add some HCl to this water, you would now be increasing the hydrogen ion, so it would be an acid. So anything that would increase the hydrogen ion concentration would be an acid. Right now, with pure water, the OH and the H is equal, and OH is considered a base. So anything that you would add to water that would increase the OH part would be a base. And that's kind of the basis of the pH scale. So bases would decrease the number of hydrogen ions, it increases OH. So bases are just kind of as bad as acids. We tend to think of acids as being dangerous. So a really strong base is NaOH. And if you were to put that into water, it would form Na plus and OH minus. And so it's a base. An example of a base, a really strong base, would be Drano or lye. All those things you kind of lock up in your kitchen cabinets and stuff are very strong bases. And so they are very toxic, just as a strong acid is toxic. So anything that increases OH is a base. Anything that increases H is an acid. One of the things that's particularly confusing about pH is that pH is a measure of the concentration of hydrogen ions, but it's called a negative log scale. So what that means is a log is when you're dealing with very small numbers, it's a way of converting them into another number. So for example, when you have 1 liter of water, a liter is a little bit more than a quart. You have in that water, this is the number here, 0.0000001 gram of hydrogen ions. A liter of water weighs 1,000 grams. So you can see only a small amount of that water has ionized, and it's 0.000 with 6 zeros grams of water. So that number is really hard to write all those zeros. And so if you can turn that into scientific notation, you probably learned this someplace in school, and you move the decimal place over. And so that's the same as 1 times 10 to the minus 7. And then for the pH, we get rid of that. The pH is based on this exponent here, and then we just convert it to a positive number. So the pH of water is 7, which is, since water is neutral, that means anything that has a pH of 7 is neutral. Now, as you get more hydrogen ions, if you think about it, the hydrogen ions increase, so this concentration increases. So instead of having, for example, 6 zeros, suppose you only had 4 zeros. So that would be 1, 2, 3, 4. So that would be 1 times 10 to the minus 4. So that means the pH equals 4. So because it's this negative log scale, the smaller the number, the more acidic. So a pH of 4 is more acidic than a pH of 7. And each number represents a 10 times change. So if you go from a pH of 7 to a pH of 4, if you go to 6 is 10 times, 5 is 100 times, 4 is 1,000 times. It's 1,000 times more acidic than a pH of 7. So anything below a pH of 7 up to a pH of 0 or down to a pH of 0 is an acid. And anything above a pH of 7 up to a pH of 14 is a base. So the lower the number, the more acidic, the more hydrogen ions there are. That's always a little bit confusing because you tend to think of a lower number being smaller, but because it's that opposite of a negative number, it's actually bigger. So a pH of 2 is more acidic, has more hydrogen ions than a pH of 3. As you go above 7, you're getting more basic. And so a pH of 14 is more basic than a pH of 13 and less acidic. And this just gives you some examples of some substances you might be familiar with. So here, pure water is a pH of 7, and that's where the number of H's and the number of OH's is equal. If we have an acid solution, we have more H's than OH's, and some weak acids are up here, strong acids like battery, lemon juice. Gastric acid is your stomach acid. That's actually very acidic. Coca-Cola, vinegar, tomato juice, etc. And then the basic things would be, our tears are a little bit basic, but then strong bases would be ammonia, bleach, oven cleaner.